We'll start firstly with Professor Vasilis Fthenakis, who is from Columbia University. He joined there in 2006 as a joint appointment with the Brookhaven National Laboratory, and he founded the Centre for Life Cycle Analysis with the objective to guide technology and energy policy decisions. He's done a whole lot of other things which are in there, but one of which are in his bio, which you'll find on the website. One of the key things is that he was instrumental in setting up the International Energy Agency PVPS task on sustainability. That's PVPS task 12, which has led to a whole lot of great outcomes looking at sustainability for photovoltaics. He's a recipient of several honours. He's written a number of books and 400 plus papers. He's the editor and associate editor for a number of journals. So he's a really well qualified person, and I'm sure they'll be giving us a great presentation. So please welcome Vasilis Fthenakis. Thank you.
Thank you, Ken. I may add that I think I'm the only one from the United States, so I feel especially honored and humbled by this opportunity. And I wanted to thank the committee for inviting me, and my host, Professor Richard Korkis, for his guidance and his good company. I'm the first time in Australia. I like the city. I like the people. So you see actually the story that I'm going to present today, and it follows pretty much my professional evolution over perhaps 40 years. So let's start with the sustainability framework as I see it. And this simple triangle, I think I like that simplicity that I think is the ultimate sophistication, that we're talking about sustainability along three basic dimensions: cost, resource availability, and environmental impact. With cost, we're talking about affordability, not only by the rich in Australia and the US, but also in the developing world. 1 billion people don't have access to electricity. It has to be affordable. With environmental impact, we're talking about local, regional, global impacts in a comparable context, always comparisons with other technologies, other power generation technologies. And with resource availability, we're talking about in a comparable context with materials, but also land and water in a multi-generational horizon. We have to see of perhaps not to deplete resources for our grandchildren, all of this together. So let me actually kind of split this evolution, as we all know it has been happening, in three stages: the infancy, junior, and adult. And I will actually describe my role in those that I happily actually was able to play. Initially, at about 1980 to about 1995, that I call the infancy period. At those years, the market was only niche markets, some actually small systems in places that are off the grid, like in Bolivia, for example, in a village. It transformed the lives of these villagers. Beautiful architectural designs, the ECN roof there in the Netherlands. The cost was not a big factor there. They were niche markets. And also, we're not looking into materials and availability and so on. The environmental impact focus was on maintaining safe research facilities and safe startups, because companies were starting there looking and were working with a lot of chemicals, and we were actually helping them in maintaining the facilities. And those years, I was working at Brookhaven National Lab until about 6 years ago, actually operating a photovoltaics environmental health safety center under the auspices of the US Department of Energy. The department wanted us to help the industry to be safe, to help the research labs to be safe. So we're doing a lot of safety audits, walkthroughs, and so on, and a lot of studies kind of proactively looking into hazard identification, hazard characterization related to new materials, new processes, new technologies. And we developed those during those years, a bibliography of about 170 publications dealing with toxicology, with waste management, with industrial hygiene, different environmental health and safety issues in, again, the new evolving technologies. And this bibliography helped us very well in later times when a lot of questions were asked to have the answers ready. It helped us very much. Now, the junior, perhaps 1998 to 2005, there our investigations, sustainability investigations, were expanded, looking into. Actually, we compiled standards for the industry, EHS standards for the industry those years with the Department of Energy. And we started looking into the energy use, into material use in facilities and the peak shaving markets. That was actually the new market. And we entered by about 2005, what is now actually still the adult phase. The adult phase lasts longer. Hopefully, it can last many more years. Then we looked into potential environmental impacts of large solar farms, a real issue. Taking a lot of acres, a lot of hectares, thousands of those in the multi-100 megawatt actually levels, and we looked into the potential impact on the environment. Recycling came under the radar there, because we started perhaps thinking of critical elements like tellurium, cadmium telluride, and indium, gallium, in CIGS, germanium, silicon, that they were critical minor elements in the production of base metals. So we have to look into those actual resources, and also starting to look into the energy use and energy return on energy investment. And why we done that? There were some real issues, but there were also a lot of perceptions that we need to address, like photovoltaics pollute the environment when they operate, a perception of a myth, obviously. We know, but we have to address that proactively. Energy return on energy investment is too low, that photovoltaic deployment uses too much land, perhaps a real issue. I'm going to discuss this a little bit. That power plants, photovoltaic power plants, create a heat island effect, perhaps a real issue. I'm going to discuss that as well. And that PV growth is constrained by material availability. Again, the bibliography we had early on, it helped us very much. And of course, we continue until these years to publish and dissemination, go to extra step as all scientists that are actually in the climate change mitigation area, we have to do. We have to disseminate the results of our research, not to stop at producing the research, but disseminate effectively as we can, as much effectively, the results of our research. With many publications, and several publications take a cover, actually covers on high impact journals, papers, magazines, and so on. I think a publication that it was the first one that it combined the three dimensions of sustainability, the cost, materials, environmental impact for the US, was published in Scientific American in 2008, and it was actually translated in 8 languages. There we show that we have a lot of resources in the US and that it can be very affordable. And actually, our projections in terms of the cost, they were conservative. The industry did better than us. We projected that by 2050 would be 1.2, $1.20 actually the system cost, and it's already less than $1 by now. Now, environmental impact. Excuse me that I'm going a little fast, but it's only 25 minutes and I have to cover so many things I think I do. So environmental impact is actually looked at with this life cycle assessment framework that you see on this figure. So looking at the impacts, not only during operation, but all the way from the beginning, taking the materials from the ground, mining, the refining, the construction of the cells, construction of the structures, the inverters, the operation, to the end of life, and with the potential of recycling or disposal and so on. And there are basic metrics, as you all know, energy payback times, greenhouse gas emissions, toxic emissions, resource use, and so on. Now, there are a lot of data there, but there were data missing on potential accidental releases, like if you have broken and abandoned modules in the field, could materials leach out? There were a lot of studies there. We also did some original studies on the potential of emissions from fires. If you have rooftop modules and the house wouldn't actually frame houses, they can have fires several times, statistically in the US about 1 over 10,000. And if you have the fire that engulfs the roof, then the PV system could be also exposed there. So this is actually a topic that I could have a full lecture on it, but I'm just giving you a synopsis there. We did, actually, we are cutting modules, cutting telluride in this case, because it's the one that has a toxic precursor there, cadmium, and we were cutting those in pieces and we're exposing them. Actually, we're heating according to protocols up to 2.5 hours, according to American Society of Testing Materials protocols, and we're measuring emissions with two scrubbers in a airtight actually reactor. And we're doing a lot of analysis and so on. One type of analysis was to look with with X-ray fluorescence at Brookhaven National Lab synchrotron to look into a molten glass. What you see here in this picture, actually, there are two glasses, front and top, then they have fused together, and And here in the center, you have everything else. You have the semiconductor and the metal elements, and you have the EVA. It's black because the EVA has been combusted by then. And we saw that very little cadmium will come out because it's sequestered actually there very effectively. About 0.5% can come out before the two sheets actually melt together. And this direct emissions of cadmium, we'll compare, again, everything that we do, it is in a comparable context, comparing with coal. And normal emissions from coal in the US, all the US coal power plants, they're equipped with bathhouses and or ESPs, 99% efficient. Still that actually 1% that goes through normally is about 400 times more than all the cadmium emissions in cadmium telluride. Recycling is very important. And I'm very glad that we had actually two sessions here that are devoted to recycling. We developed the technology early on, again, under the auspices of the US Department for cadmium telluride recycling. Cadmium is an issue, and tellurium is also an issue because of limited availability. So you wanted with this recycling actually technology to clean the streams of cadmium and recover as much tellurium as you can. So it starts with fragments. We're getting this from the manufacturer, produced from hammer mill, and we're exposing those to a dilute solution of sulfuric acid and peroxide, quite dilute. Again, less environmental impact, quite dilute, less cost. Very cheap, actually. We plan for something like that for a cost of about not more than 1 cent per watt. So lithium produces glass. I call it clean glass, but actually it's not completely clean glass. And we are now actually working with Pablo Diaz, with his company. We have a big proposal. And part of this is to clean the glass better so that it can go back into float glass, into rolled glass production, and have a closed loop there. So far it doesn't. It goes into packaging. It's kind of downgraded. Now, the leachate will go through a set of ion exchange columns. The first will retain copper, the second cadmium. At the end, you have a tellurium-rich liquid with precipitation. We get a tellurium dioxide. Rinsing of the first gets the copper, rinsing of the second gets cadmium, and you can recover those, and then you purify and get them back into the cadmium telluride production. Now, we can see here the integration of those three basic dimensions of sustainability and how recycling helps on all of those. Cost, of course. I mean, you have a secondary resource there with recycling, and that relieves the pressure on the cost that it happens with imbalance between supply and demand. And obviously, you have more to use there with recycling, and it also it helps very much in lowering the environmental impact. You're using less energy, less materials when you recycle, and you avoid landfilling that has risks when you recycle. It helps very, very, very much. Now, one of the myths, there are so many that we addressed, is that PV uses a lot of land. Now, of course, it does, the plant. It uses less than a coal plant. But in the life cycle context, which is the real context to look at things, you have to take all the land used in the life cycle. So by accounting the mining of quartz goes into silicon, but accounting the mining for coal that goes into coal, we found, and several other studies after this was the first study, I recall, they also validated those results, that you have actually better use of land for PV in the Southwest than the land used in the in the coal industry in the United States, based on historical data. Those are not the kind of projections. Based on historical data from Oak Ridge Argonne National Lab of the actual land use in surface mining, 75% in surface mining. And the picture is better now because this comparison actually is based on, I think, 40% efficient modules. And now we have 20% efficient modules, so even less land per functional unit gigawatt hour. And the land use is environmentally friendly, very big, actually difference than the land, the damage that you have when you save actually mountaintops with surface mining. It's very friendly. A real issue is though, with the very large solar farms that they can take thousands of acres, how to protect wildlife. And I mean, there is a lot in the Southwest, in the Sonoran, in the Mojave Desert and so on. But they're not really completely empty of species. I mean, you have species there and you have an ecosystem. So we work with SunPower early on with the big actually plants and First Solar, and together actually we develop ways of mitigating, actually preventing effects that can be preventable on species with avoiding sensitive areas, minimize the impact on the ground, allowing for corridors for the migration of species in those big solar farms, and maintain and improve vegetation that is the habitat for several species. So actually, I think that with those studies by SunPower First Solar, we know more about biodiversity in these areas that we knew before these actually studies were done. So it helped. Heat island effect also, I mean, if we have 20% efficient photon to electron modules, 80% dissipates in heat. So you expect that you have increase of temperature. You have actually a hotter environment there. What we looked with the CFD modeling, and the modeling actual results were validated against the data with actual temperature measurements in the Sarnia 80 megawatt plant in Ontario, Canada. This heat island actually effect is not really a heat island because it cools at night. It's not a permanent one. It cools at night, and also with height and with distance, it dissipates completely to the background temperature. So it's not an issue really, other than inside the solar farm, you can have a significant increase of temperature. Now, energy payback times, that is the kind of metric that we all understand, is for how long the system should operate to produce all the energy that it has been used in the life cycle. Early on, we had, inefficient systems, and we were using a lot of cement on the basis. We had 640 micron silicon wafers, not a very good material utilization. Early on, the energy payback time was bad, but by now, and actually perhaps this picture here is 5 years old, the energy payback times can be down to a half a year. So a system that operates for a half a year, depending on the area where it operates, and you can see that it's a strong function of the solar irradiation, it could give you actually all the energy back that it was used. Now, what intrigued us and got into this area at about 2004, at the beginning of the adult age, many inconsistent results in the literature. People were using actually in studies of 2000, they were using 1990 data, 1999 data, old data because they used to be there. So completely actually consistent, different use of methodology. So that's why, as Ken mentioned, we actually found it under the EIA auspices, the International Energy Agency Task 12, and with analysts in 14 countries, we developed guidelines and assumptions that make, I think, the whole literature results to be more credible. Now, the evolution continues with established technologies. In silicon, for example, taking 5 years between 2015 and 2020, we have a betterment of about 45% for the energy payback times in crystalline silicon because of efficiency increases from 17% to 20.5%, but also, most importantly, because of much better material utilization. We have diamond cutting, we have actually thinner cells and a lot less kerf loss, down to 65 micron from 145 that we had before with the multi-wire slurry type of source. So you can see this here. Energy payback time, it has in numerator, it has that CD, that's cumulative energy demand. In the denominator, it has the energy production. And you can see here that in single crystalline silicon, the big contributors in the energy payback time early, here in the deep orange and the yellow, is the Czochrawski ingot production and the wafer production. Now, when you have much less curve loss, everything actually decreases. Everything decreases. And you have also the impact of the increased efficiency. Now, these improvements on energy payback times continue with emerging technologies like perovskites. And you can see here, this is a little busy actually slide. Here, these very low numbers correspond to 4 single junction perovskite technologies. One is the roll-to-roll gravure printed type of technology on a flexible substrate. And then we have actually 3 technologies on rigid substrate glass, 2 spray coating, 1 with vapor deposition. And here at the other end, we have 3 tandem technologies. They all have much lower, actually, cumulative energy demand than silicon or thin films. So, but again, to translate that into energy return on energy investment, we have to have comparable time horizons. So this is without assuming really that we have the same longevity in perovskite and silicon. Perovskites are much better than silicon or thin films. Now, remaining challenges and new opportunities. Dual use of land is actually a challenge and an opportunity. And in some areas, like in the south of Italy now, because they don't have that land availability that we have here or in the US, I think they only permit solar farms in conjunction with agriculture, agrivoltaics, which is a good thing, I think, to do. And they can provide additional income to farmers and so on. And also, we're looking here in the US and in other places for ecosystem services, like pollination, for example. We have actually the carbon soil absorption in those areas. Habitat actually improvement. We're looking for ecosystem service from solar facilities. Now, what is remaining though, and again, the associated opportunities, the variability of solar, that is the remaining issue that we all working on those days. What is the opportunity? Variable electricity, you can have abundant, maybe excessive electricity, you can do other good things and address other actually needs of humanity. Like what? Water, food, environment. This is actually a list by the Nobel laureate in chemistry, Dick Smalley, 1996, for his inversion of fullerenes. You know, the carbon 60, carbon 80, actually built in black of nanotechnology. Actually, in the US, by the US Congress, he was declared as the father of nanotechnology and put energy at a list there with descending priority. If you have a solution for energy, abundant, clean, cheap energy, you can address to certain degrees the other actually challenges below. Obviously, with water, desalination, using energy, and pumping energy inland. And food, chemicals, ammonia, and so on. Environment, obviously, because clean energy. Now, at my center at Columbia University, for many decades, we're looking at Brookhaven National Lab, we're looking only at energy and the environment. Over the last 6 years, we included in our investigation the water. So we look into energy, water, environment nexus. And what can happen there? We're looking actually into new opportunities in industries that use a lot of energy. 2 of those are desalination, use a lot of energy, and actually the cost of energy can be 50, 40 to 60% of the cost of desalination. Hydrogen, the same thing, green hydrogen electrolysis, a lot of energy, and the cost of energy can be more than half of the cost of hydrogen. Now, what can we do with this? And of course, both of those actually systems, desalination and hydrogen, they pollute a lot because they use a lot of energy, and currently it's fossil energy. We have about 95% of the hydrogen in the United States is produced by gas, steam, methane reforming. About 12 actually kilos of carbon dioxide per kilo of hydrogen produced. And we have big CO2 emissions on desalination as well. Now, what is really the way we looked into that? To develop designs that are variable. So variable desalination in a dynamic actually operation, variable hydrogen production, dynamic for dynamic operation so that it can handle to some degree at least the variability of solar energy. This is what we have been doing. And for example, for water electrolysis, there are two commercial technologies, that is alkaline and PEM, the proton exchange membrane. The latter is more flexible. Those devices, those actual equipment, the electrolyzers, they can be switched on and off within seconds. And it can work in different energy, in different actually current density levels. So it can always actually, it can be more flexible. Typically, they're operating at about 1.7 ampere per square centimeter at an efficiency of about 85%, but they could operate at higher current density at loss of efficiency and some loss of degradation. I didn't have time to describe here, but if you have more electrons into the system, you can produce more hydrogen, and there can be a sweet spot. As you can see here, this is a study that we've done using actual electricity prices from the California ISO, just taking advantage of the electricity price variation. And we found that operating at about 3 ampere per square centimeter, it can give you a lower levelized cost of hydrogen than operating at the standard. And this takes into account the effect of degradation and the effect of the lower efficiency operating at higher current densities. And you can see down here, actually, the end result that operating dynamically, it can take the price down from about $2 per hydrogen, per kilo of hydrogen, down to 1.5. So going closer to parity with SMR. Now, another type of investigation is actually looking into systems that include, they have desalination and the hydrogen coupled together. How and why? Because hydrogen electrolysis actually of water is based on demineralized water. The current technologies, both alkaline and PEM, need deionized water. So you need kind of desalination. Typically, they use reverse osmosis. Is the lowest actually cost membrane-based type of desalination technology. But and typical electrolyzer operating at 1.7 ampere per square centimeter, it generates about 7 kilowatt hour per kilo of hydrogen of waste heat. When we operate it at a higher current density, you have lower efficiency and you have higher waste heat, higher levels of heat. So we found that this heat here is more than enough to implement thermal desalination technologies, like low temperature, multi-effect distillation that works well from 60 degrees to 70, 80 degrees Celsius, and also membrane distillation. It can work. So you can have an autonomous system. You can have that in a platform in the sea, and you don't need any actually electricity grid connections or any kind of electricity there. Maybe something to start with the diesel to start the system. But after that, you can have autonomous system that uses the waste heat from electrolyzer into powering the desalination unit for producing the deionized water that you need for hydrogen production. Okay, so perhaps I went too fast, but then I have more time for Q&A, so that's a good thing. The PV industry, as we discussed, still evolves on all sustainability dimensions. It's still getting better and better. And I'm lucky and happy to be part of this evolution. Now, early on, the focus was on maintaining safe facilities. The focus is still there, okay? Especially if you have new technologies, new startups, that focus never goes away, okay? Environmental health, safety, vigilance, and proactive approach must continue. Recycling end of life systems becomes an important aspect of sustainability. And we have actually PV cycling in Europe. We're trying for decades now to implement something similar in the US. I think it's happening now. First time the DOE actually gave a significant call on actually optimizing recycling research and so on. So we're hopeful. And as I mentioned, actually, UNSW-based solar cycle company is now working in the US for the implementation of solar cycle in the US. And but low-cost solar, and this is really the future, as I see that, of sustainability. Low-cost solar energy creates new opportunities while addressing humanity's big problems, like availability of water and energy for 24 hours. With the carriers like hydrogen, for example, from hydrogen, we can go to liquid fuels and so on, as you know. Thank you.
Thanks very much, Vasilis. Fascinating coverage of a lot of really important information. We have time for a couple of quick questions. Up the back there.
Hello. Hey, Vasilis, thank you for the presentation. I was looking at the results that you showed from 2012, if I'm not mistaken, of how the energy payback is about half a year now. That's obviously looking at energy only. If we look at other metrics from an LCA, such as eutrophication, et cetera, toxicity, what does that look like? When is it the payback time for PV systems? Because if we can look at it holistically, it's even better, right?
Yeah, right, Pablo. Actually, it depends. It depends. I mean, typically, from greenhouse gas emissions, what we saw there, the energy payback time gives the picture of energy. And typically, for a fossil-based energy grid, a fossil fuel energy grid, the greenhouse gas emissions, they're proportional. Now, ecotoxicity, human toxicity, and so on, it can be different. It can be different. So, for example, even if you look in perovskites, or if you look in some actually elements in cadmium telluride in other thin films, you may have more human toxicity, more ecotoxicity. So there can be actually different perhaps description among different solar technologies. But if you compare solar technologies with other power generation technologies, the picture for solar is always better, always better. And this is what is the comparison with alternative, comparison with coal, with gas, okay, with nuclear. Maybe people think that nuclear perhaps has better greenhouse gas emissions, lower than solar. No, it's not. Looking actually taking the fuel enhancement ratio in the United States between centrifuge and diffusion, PV is much better than nuclear. So in all metrics, solar is better than fossil technologies and nuclear.
Thank you very much.
Sure.
One last, Richard, hopefully a quick one.
Thanks, Vasilis. Really interesting talk. Thank you, and thanks for your leadership over these years. As we try to use one or to have impact on one aspect of environmental impact, that is, we try to reduce the amount of materials going into PV modules, for example, we perhaps run a risk of reducing reliability, reducing the lifetime of them. Have there been any systematic studies of that interaction and sort of helping with one leg of the stool? Do we knock it down on another leg? Sorry, that's a really bad analogy, but you know what I mean.
No, there are actually studies on specific issues, like, for example, silver and so on, right? I mean, we try to get in towards silver-free cells. Now, is it bad or good? It would be actually good for the environment because silver is toxic. It could, though, come with a little penalty at some point in the beginning if we have copper that we don't have really the performance that we want. But I think everything, you remember what is at the peak of my triangle is the cost. The cost is very important. So the industry is driven by cost, and I think that's a good actually guide. Of course, I mean, durability and so on, it comes also with that. So now the industry is looking into longer lives of modules. Perhaps they don't try so much to reduce the use of materials that they are not critical, okay? But through recycling, and if the industry subscribes to recycling, you address that. So there is a multifaceted issue, and I don't think that's the same for all technologies. So technologies that have critical materials, actually, they need probably they need a reduction of the use of that. So I guess, for example, cadmium telluride, they could go from 3.2 to 2 to 2.5. They can micros layer. They can go all the way to 1 micron, but maybe they don't want to do that because then we'll have a slower throughput. It has to be, the vapor deposition will be actually slower if they try to have a uniform actually layer over 2.4 to were meters of only 1 micron. So it will be a cost issue there. But there are studies, specific cases.
Thank you.
Well, thanks very much, Vasilis.
Thank you.
Vasilis will be around for the rest of the
Yeah.
day, so if you've got any further questions, catch up with him at afternoon tea.